Now we're going to continue with the Poincare patch and Poincare coordinates in de Sitter space. Another possible solution of this equation that 8a bxa xb equals 2h minus to the second power is the following. We can write hx, well, this can be related to this, plus hx d squared equal to 1 minus h xi plus, the reason for the notations will become clear in a moment. So we can define this to be equal to this, h tau plus, and hx1 squared plus hx d minus 1 squared equal to hx plus I squared 2h tau plus. So using this, we can write the following. Well, this can be now solved as hx0 equal to hyperbolic sine of h tau plus hx plus I squared over 2 exponent of h of tau plus hxi, this then will be solved like this, hxi plus to the exponent of h tau plus, where I, both here, here, and here, and here, is ranging from 1 to d minus 1. And finally, hxd, which solves this, so that together with this, so this equation is minus hyperbolic cosine of h tau plus hx plus I squared over 2 exponent of h tau plus. So if we plug now these expressions into the ambient space Minkowskian metric, then we get metric induced on this space of the form ds plus squared equal to d tau plus squared minus exponent of 2h tau plus dx plus vector squared. This guy is just this thing here. Now, so the problem with this metric and with these coordinates, one can see immediately is that minus x0 plus xd, as follows from here and here, is nothing but minus 1 over h exponent of h tau plus, which is always less than 0, which means that x0 is always greater than xd. So these coordinates do not cover entire, unlike the previous coordinates which we have been considering, they called global coordinates and they cover entire de Sitter space, entire hyperboloid. These coordinates cover only half of it. So if those coordinates were covering all of this hyperboloid, these coordinates cover only upper half of it. Like we have to cut it by a plane like this, and these coordinates cover only that half. And these coordinates are called Poincare coordinates. Well, Poincare coordinates we will define in a moment. This is already almost Poincare coordinates, but this half of de Sitter space is called Poincare patch. In fact, the other half can be covered by similar coordinates with a bit different coordinate changed from this, and then there we have the metric like this, ds minus squared, d tau minus squared, minus 2h tau minus dx minus squared. So these are expanding coordinates, expanding Poincare patch, and this is contracting Poincare patch. Look, this factor says that spatial sections are expanding. So in this half, spatial sections are expanding, while in this half, spatial sections are contracting as the time goes by. So on the Penrose Carter diagram of this rectangle, where, so there are different choices for Poincare patches, but what we did is that we have chosen, these are light-like lines, which are cutted by this plane, which divides de Sitter space on two halves. So these are light-like lines. So this is a 90-degree angle here. And one can see that this is expanding Poincare patch. And this, remember, this is glued to this. This is contracting Poincare patch. And in fact, we can cut out expanding and contracting, different expanding and contracting patches from the de Sitter space by different choices of this plane, because we can, this apex of this angle, we can choose here, and this will be more or less the same situation, equivalent to what we are discussing here. And one can see that constant tau plus slices are just this kind of lines, and constant tau minus slices are these lines. And as time goes, this is tau minus equal to minus infinity, and this is tau minus equal to plus infinity, and this is tau plus equal to minus infinity, and this is tau plus equal to plus infinity. So we have expanding Poincare patch, spatial sections are expanding, and here is contracting Poincare patch, spatial sections are contracting. It is convenient to introduce so-called conformal time here. So if in this metric, and in this metric, we make the following change of the coordinates, h eta plus minus equal to exponent of minus plus h tau plus minus. So for h eta plus, we have here minus exponent of tau plus. For eta minus, here we have exponent of plus h times tau minus. In both cases, from this and this metric, after this change, we obtain the following metric, ds squared plus and minus look both the same, more or less, with one crucial difference, which I'll explain in a moment. So d eta plus minus squared minus dx plus minus squared. So this is these are Poincare coordinates for the Poincare patch, and constant eta, this is also constant eta slice, and this is also constant eta minus slice. But what is important, at past infinity, eta plus is equal to infinity. At future infinity, eta plus is equal to 0. This follows from here, because when here we have minus sign in the exponent, tau equal to minus infinity gives us infinity here, and tau equals to plus infinity gives us 0 from here. And here we have a reverse situation, that eta minus is equal to 0 here, and eta minus equal to plus infinity here. So basically, expanding and contracting Poincare patch obviously can be obtained from each other by time reversal, reversing the time from tau plus to minus tau minus, we obtain from expanding contracting patch, and vice versa. And that is exactly what happens here. So, and the boundary between these two patches is just these two straight light rays. So the past infinity of expanding Poincare patch is light-like, and future infinity of expanding Poincare patch is also light-like. And one final two final points about de Sitter space. Perhaps we can say them as follows. One thing, that in these coordinates, the hyperbolic distance in de Sitter space, in both cases it looks the same, just with the change, with the use of eta plus or minus and x plus and minus. So the hyperbolic distance between 2 points is like this. x2 squared divided by 2 eta 1 and eta 2. So this is a hyperbolic distance, and basically that's it. One probably final comment is that one can cover entire de Sitter space with this unique metric, with one eta parameter here, which coincides with eta minus here and eta plus here. But inconvenience of this metric is that there is a jump of the values of eta as we cross these lines. So these coordinates are not so convenient as the global coordinates to cover entire de Sitter space. One final point that I want to discuss about de Sitter space before continuing with anti-de Sitter space is a notion of physical and comoving volume. Like, what is de Sitter space basically? Well, consider a balloon which towards past infinity is expanding. So from past infinity to the center of the de Sitter space, to the neck of the de Sitter space, is shrinking. So basically, at every given time, we have a balloon of different radius. And also to future infinity, it's expanding. So this is a three-dimensional de Sitter space if we are talking about two-dimensional balloon. If we talk about circles, this is a two-dimensional de Sitter space. So consider like a points spread over de Sitter space, say like 4 points here, the same points. You see, as the time goes by, their number is not changed. Well, this is like a dust, but their density is increasing, while towards here it's decreasing, but then starts its increase again. And if we draw a line, a circle here, the same circle, and trace its change in time, the area enclosed by this circle, or volume enclosed by in case of multidimensional balloons, this will be spheres. The volume enclosed by this will be physical volume. This is exactly physical volume. So spatial physical volume. Remember that de Sitter metric always in spatial sections has here either cosine squared ht over h squared d omega squared d minus 1, or in Poincare coordinates it's either 1 over h eta plus minus squared dx plus minus squared. So the volume measured with respect to this metric is the physical volume, is exactly physical volume. So we just dv. So the volume measured by this coordinates times the volume factor which follows from here. So we have d minus 1 v following from here or here, multiplied by the appropriate power, d minus 1 power, of this scale factor. Well, for example, for this case, it's just cosine ht divided by h. And for this case, it's 1 over h at plus minus. So this is a physical volume. It's changing according to how the physical distances are scaling. And the density, as we see, of the dust is changing accordingly, like inverse of this. So when it shrinks, the density is increasing. When it expands, the density is decreasing. But this volume, which is multiplied by multiplying this factor, is called comoving volume. comoving volume. So somehow to obtain it, we subtract this factor. It's not, I don't understand how to draw this comoving volume on this diagram. It's not the same as if you put it say a solid object on this sphere and like it doesn't change its size. So like for example, we put it something like this. It doesn't change its size and it shrinks somehow and then expands back. No, this is not the comoving volume, because in that case, if this is a solid line whose size is not changing in time, then the number of points will be changing within this line. Like for example, as it shrinks, number of points coming into this line will be increasing, and as it expands, number of points is decreasing. The density per comoving volume remains unchanged, number density. It is like always 4 points. You see, the density with respect to this is always given by 4 points. But with respect to comoving, it doesn't change. With respect to the physical, 4 is attributed to the bigger distances, and that's the reason it is decreasing. I hope it's clear what I mean. With this, we finish our discussion of de Sitter space.